All right, let's hope that Snaps Pro is not actually running in the background, undermining everything we're about to do. Yeah, so the other recording software. Hey, so guys, here's how we're going to wrap up this chapter, but not this unit, which means that chapter 15 summaries will be due when I see you after the long weekend, because our next and last chapter is 15. Yeah, because guys, no school Monday, see you Tuesday. So guys, what we're going to do today is we're going to finish this conversation by going back to rate laws and talking about the way we began the unit. Because you may remember we began the unit by talking about what you learned in general chemistry, which was fundamentally there's 4 things that change the rate of the reaction. Concentration, did that to death with rate laws, temperature, surface area, and catalyst. But guys, we talked about the idea that we weren't just going to call it surface area, we were going to call it the nature of the reactants. You'll see why in a minute. But guys, what we're going to do now is we're going to talk about those other things. And if you're sitting there right now going, I'm not quite sure what he's talking about, guys, we understand that generically a rate law looks like this. And we have now done 4 days of concentration rate relationships as they are dictated by reaction orders and mechanisms and all of that, elementary steps and all of that stuff. Well, guys, what we're going to do now is we're going to talk about these guys, because those guys change rate as well. There's other things that change the rate, but mathematically, guys, those are all contained in K. So, don't miss this. Temperature. You guys know this. Temperature, and guys, I'm about to share with you an important guiding principle in AP in general. Ready? Temperature affects rate, right? Let's say it. If temperature goes up, hold on, you guys are going to be looking at Jacob, and this is important. You just got scolded by Brandon. You guys can sort this out later. Hey, so guys, seriously, temperature goes up, rate goes up. Why? Oh, bless your hearts. Guys, you have no idea how encouraging that was to hear your answer. Because a lot of people go, because K gets bigger. No. And guys, understand, you look at this and you chuckle, but increasingly over the rest of the year, you're going to find that things are going to get mathematical again. We're going to be using mathematical equations to describe chemical realities. And it's really, really easy, because you guys know the AP test is going to be drilling you for why. Explain. They are going to make you dig into what's going on in the chemistry, and they're going to ask you questions, which I'm so glad you answered well and then chuckled. Guys, they're going to ask you questions like, what effect would an increase in temperature have on the rate of this reaction and why? And you would all say, as the temperature goes up, the rate goes up. But then, guys, the mistake that many people make is they fall back on the math. And they say the rate goes up because K goes up. And if you're chuckling right now, half of you made this mistake when we were talking about spontaneity as it relates to Gibbs free energy. We had a question on a previous test that said, is this reaction? And it was about entropy and enthalpy. And guys, we got to the point where it was time to determine how would the value of G depend upon change in temperature. And all of you came back to and you described the reality with math. Guys, fundamentally, and I know you're chuckling, fundamentally you've got to understand, chemical reactions can't do math. And it's critical that you understand that. Because, guys, they're going to ask you to explain things. And fundamentally, you've got to understand, guys, mathematical equations are descriptors. They are not predictors or controllers. So if you've got a chemical reaction, you can describe how the rate goes up based upon temperature, because K changes, but that's not why the rate goes up as temperature increases. So bottom line is this: if you ever, hear this, if you ever on the test see explain or why or however they ask it, if you use a mathematical equation, you're gonna be wrong. Do you see what I'm saying? Guys, math never explains things, it describes things, and it's important you understand that. So, so you guys understand why I was so encouraged, right? Because when I ask you if the temperature goes, what happens to rate, and then we said why, and your answer was collisions. That's it. It's collisions, frequency or magnitude. Both, right? Okay, but you guys understand what I'm saying? I know I'm preaching a sermon, but guys, we got to, okay. All right, so guys, with that said, this is going to be lots of little things. We are going to now talk about the factors that influence the rate of a reaction. And so well, here, you don't need to write any of this down because we just talked about it. That's even what I wrote on the board. Just one second. That's even what, so this is all the precursors to this, right? That are simply saying, we've talked about how reaction rate, and maybe we should talk about this one because we didn't immediately. Guys, we've talked about, we've talked about reaction rates as they change with time and concentration, and they're related, right? What happens to the rate of the reaction over time? Why do they decrease? Concentrations are going down. Okay. So now we're going to talk about K. Go ahead. It could. Yeah, and I'm actually about to show you a graph. But yeah, and that would be totally fair. If then, well, how would you explain it, right? So if the question was, how does K change with an increase in temperature? I suspect the question would just stop there, and you could say the value of K increases. I can't imagine them asking you why or explain. I mean, if they did, you could say as temperature goes up, the rate goes up, and in the rate law, the only way that could happen is if K increases. I can't imagine them doing that. No, but it does bring up an interesting thing you should be thinking about. When they're writing questions for the AP test, this is hard enough as it is, right? And so when they write these questions, what they're really trying to do is write hard questions that only have one answer or explanation, because and that's why they vet these questions. I don't know if you know this or not, but when they're writing AP questions, they actually give these questions to college students before they ever hit your tests. Because this is supposed to be a college class, they want to know how these kids would do on the test. They actually normalize for that in your AP scores. And so if they offer a question and there's like 11 different answers, they're going to throw that question out. So they tend to be hard and yet simple. Go ahead, Brian. Yeah. Let's talk about them. Okay? Okay. So, guys, let's talk about these things that affect K. So, first of all, we're going to talk about orientation. This is, and you can just, this is something you want to get in your notes. We said last year that surface area was the deal. And that's true. Surface area is important. But guys, we put surface area under a larger catch-all, which was the nature of the reactants, of which surface area is an issue. And you've already established, we talked about this, that you understand that increased surface area increases the frequency of collisions because there's more places they can hit, right? You guys good on that? Okay. Well, guys, here's the deal. Even if these things hit and hit with enough energy, there's still no guarantee that a reaction will occur. This is something we haven't talked about before. Last year, we learned about this idea of activation energy. And we said if two particles collide with enough energy to get over the activation energy hump, a reaction is going to take place. Because it turns out that's not true. And this additional thing that you need to understand, which is the concept of orientation, which we're going to put under the bigger heading of the nature of the reactants, goes like this. When these reactants hit, they've got to be lined up properly. And guys, we alluded to that when me and Matt and Isabel were bonking each other with ping pong balls a couple days ago. Guys, it turns out that it's not enough for these things to just hit or hit hard or hit at the same time. They actually have to hit with proper orientation. I think you can stop taking notes when you write down the word aligned. Because guys, this is what we're talking about, and I think it'll make sense. So this is the reaction between a chlorine atom and an NaCl molecule. And guys, when this happens, it turns out that the products are diatomic chlorine and nitrogen monoxide. And so in order for this reaction to happen, we've got our chlorine atom and then we've got our NaCl molecule. And guys, this is a beautiful example of why this reaction is a lot slower than you think it should be. If you collect the rate data for this reaction, it's actually surprisingly slow, given that technically this is elementary. There's nothing going on behind the scenes. This is actually a reaction which is an elementary step. The reaction is an elementary step. It's just dependent upon collisions. The problem is this. The only way this reaction can happen is if this chlorine hits the other chlorine. When that happens, these chlorines collide, and the bond between the chlorine that forms weakens the bond between the chlorine and the nitrogen, and the chlorines leave together, and the nitrogen and oxygen depart as a new molecule. Well, guys, obviously this can only happen if the chlorines hit each other. If the chlorine, in this case, were to hit the oxygen or the nitrogen, that chlorine-chlorine bond can't form, and consequently that collision is ineffective, meaning the reaction slows down, because not every collision is effective, even if it has enough energy, because alignment is an issue as well. Does that make sense on the surface? No pun intended. Is that okay? You get the idea? So guys, now the question is this. Why are we talking about this? The answer is, this is how catalysts speed up reactions. We'll get into this in just a minute. Not next, but in just a minute. And I should be careful. This is one of the ways that catalysts speed up reactions. Because guys, what catalysts can actually do is grab a hold of molecules. How do they do that? Intermolecular forces. But guys, catalysts can actually grab hold of molecules and force them to orient properly so that reactions can happen. We'll talk about that more in a minute, but this whole orientation issue becomes especially important as we understand it in the context of catalysts, which is what we'll do in a moment. So do you get the idea with orientation? Yeah. Because the weakest bond breaks, and that's the one that weakens the most. Yeah, we're not going to talk about why, because I don't know, but that's the deal. Okay, you guys good? Good on orientation? Okay, temperature, dun, 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 there it is. So guys, let's just say it and look at it. We understand, and you already know the answer. I know you still need to write, because that's what you do. But guys, you already know the answer. When the temperature of a reaction, oh, and by the way, we should say this. Guys, the fewer, back to orientation before you write, back to orientation, the less dependent a reaction is on orientation, the higher the value for K will be. Does that make sense? Let's say it again. So the less dependent a reaction is on orientation, maybe another way to think about it is the more orientations that will cause a reaction, the more orientations that are effective collisions, do you know what I'm saying? The higher the value for K will be. right? Because the more types of collisions that can cause reactions, the faster the reaction goes. Okay, that's fundamentally makes sense. So then, guys, what about with temperature? Well, you guys did a wonderful job of this, right? Higher temperature, higher rate. Why? Collisions. And then you understand its frequency and magnitude. But guys, this is actually a representation of this graphically. And so here's the statement. This is just an introduction to the graph. But guys, this is not a graph of temperature and rate. This is a graph of temperature and K. And you'll notice that K not only increases, it increases exponentially. We don't need to worry about why. You just need to understand that, in fact, when temperature goes up, the value of K goes up. And when the value of K goes up, mathematically, the rate goes up. And now you understand none of that is important as you describe why rate goes up with an increase in temperature, because then you understand it's not the math, it's all about the magnitude and the frequency of the collisions. So go ahead.
Wouldn't it not matter whether it's K or rate because they're proportional?
Exactly, and that's the point. As K goes up, rate has to go up so long as you're not messing with concentration. That's exactly the point. Yeah. Yes. So what if we said this? The increase in K is the effect and not the cause. Right? Is that where you're going? Yeah, exactly. And that's exactly the case. So as a chemical system, increasing temperature causes more and harder collisions. That's the cause. The effect mathematically is that K goes up, or it's the description. You guys good on that one? Yeah, right. Hey, K's going up. I better get to work. Yeah, no, you get it. Okay. So, all right. So guys, we've got orientation, we've got temperature. Where are we going next? We should do this. Activation energy. Next thing we need to talk about, guys, is activation energy. So keeping with, and it doesn't have to be relative to temperature, but guys, what is it that ultimately determines the rate of a reaction? Idea? That in order for a collision to be effective, it has to have sufficient energy to get over this activation energy hump. Do you remember that? So the idea is that the rate of a reaction is fundamentally determined by, and all reactions are collision dependent. Guys, the rate of the reaction is dependent upon how many collisions hit with the proper orientation, you understand that now, but hit with enough energy to get over that hump. So this is the reaction between nitrogen dioxide and carbon monoxide. But the idea here, guys, is if you take a carbon monoxide molecule and a nitrogen dioxide molecule, and if you slam them together, and if they don't hit with enough energy to get over the hump, they just roll back down. Remember the putt-putt analogy? They just roll back down as if nothing happened. So the rate of the reaction is determined by the number of these collisions that get over the hump. Notice in this example, they're also giving you a little bit of a representation of orientation. So guys, for this to happen, the carbon has got to hit, oh gosh, I wasn't in writing mode. Guys, the carbon has got to hit one of the oxygens. If it hits the nitrogen, that ain't going to work. Independent of orientation, though, it's got to get over to get back down. Is this coming back to you? Is that okay? So guys, let's talk about some things then that we need to add to our conversation. So first of all, this, and I would encourage you to include this in your notes. It's the term transition state. And actually, you know what? There's a related term that they'll allow you on the AP test. Activated complex. They are the same thing. So guys, the transition state or the activated complex are the same things. Isn't this more of a biology? One of them is more prevalent in biochem. Transition state. So guys, and frankly, it probably comes down to who your college professors are. Some will call them transition states. Some will call them activated complexes. But guys, by definition, what these are the arrangements of atoms at the apex of the activation energy curve. Do you want me to say that again? The arrangement of atoms at the apex of the activation energy curve. Right before they change or don't. Right. So if they have enough energy to get over the hump, they go to change. If they don't have enough energy to get over the hump, they go to don't. They go backwards. They go back to where they were. But at the peak of that, the apex where they could go either way depending upon energy, that is what is called an activated complex or a transition state. Guys, I frankly don't even remember learning about these until I hit my sophomore year in college. I remember learning about them a lot in organic chemistry. You know, I'm suppressing those memories, but that's where it came up. So guys, we understand that. Other things that I'd like to talk with you about just to make sure we're okay on this. First of all, looking at this reaction, is this reaction endo or exothermic? How do you know it's exothermic? Products are below reactants, right? We even see, well, hey, they even gave it to us, remember? Negative delta H's are exothermic. Is that okay? Okay, now guys, this is maybe a new thought, depending on which class period you were in with me last year. I remember talking about this with some classes, but not all. So the idea is this. We've got the forward reaction, and then we've got the reverse reaction. And the activation energy for the forward reaction is this. It gives you the number 134 joules. But now, guys, because we've talked about reversibility and spontaneity, remember chapters 5 and 19, because we've talked about reversibility and spontaneity, we can talk about this. This reaction is exothermic. Will it tend to be spontaneous? Yeah. What are the two factors? And then that's why I use I like that you're saying tens. Depends, but that's why I use tens. So guys, relative to enthalpy, what's the other thing that determines spontaneity? Entropy, which is disorder. But relative to enthalpy, would you expect this reaction to be spontaneous? Yes, right? Because it's exothermic. And it's not only exothermic, I would suggest that it's hugely exothermic. Now let's bring in entropy. What are the chances that you are going to have an offsetting decrease in entropy that might keep this reaction from being spontaneous? Pretty small, right? And if you remember, guys, our enthalpy changes tend to be on the order of kilojoules, and our entropy changes tend to be on the order of joules. So we're talking about basically 250,000 joules of disorder, right? So, because this is, I mean, if we're going to convert this into joules, oh my gosh, it's almost exactly. So guys, that's 250,000 joules of heat that are being given off. In order for this reaction to be non-spontaneous, there'd have to be an offsetting 250,000 joules per mole of decreased disorder for this thing to not be spontaneous, neglecting the fact that we have to multiply by Kelvin temperature, but you get the idea, right? The chances of it are pretty close to zero. Well, guys, we can see another reason for that. Let's talk about reversibility. So, guys, if a reaction is spontaneous, what does that really mean? Well, it means it's spontaneous in the forward direction, right? Can it go in the reverse direction? But will it? Not on its own. Guys, remember that important idea that reversible and irreversible doesn't mean can't go backwards, right? So if we've got a reaction, this is the direction in which it's spontaneous. Can we make it go backwards? Yeah, but guys, look at the problem. This is the activation energy for the reverse reaction. That's why it doesn't go backwards very well or very easily. Because guys, if we're going to drive this reaction backwards, we not only have to account for the activation energy, we've also got to account for the energy that's being lost because it's exothermic. That's why it's less likely to go backwards. Yeah?
I also have a question. When you're putting it backwards, if you're plugging in like 360
Yeah.
is it going to want to go back to the products?
It will. Assuming that, well, so we got to be careful. You've been protected from a lot of this so far. Guys, Ethan's question is, will it necessarily go back to products? Reactants. Will it necessarily go back to where it came from? And the answer is, we hope. But the problem is, and this is something we don't talk about in AP, in general chemistry. Many times, these reactions will go places we don't want them to. They're called side reactions. They're called competing reactions. They're called contaminants. And frankly, it's one of the things that makes being a chemical engineer so fascinating is in our neat, sterile little world, reactants turn into products. If these are our reactants, these are always what our products will be. The problem is that the world doesn't work that way. A lot of times you put in the same reactants and you could get different products. And there are ways of changing that. Catalyst is one. But one of the things you do as a chemical engineer is figure out how to take reactants and only get them to turn into the products that you want, because those are the things your company will sell and make money. And all of these side reactions are lost profit. And so it's one of the things that makes being a chemie really interesting is you learn to tweak reactions to make them increase their yields. But the answer in this, so the answer technically is no. It could go somewhere else, but the answer in our world is, oh yeah, they always go back there. You guys good? Okay, so guys, where are we going to go from here? Well, guys, what we're going to do now is we are going to talk about this. So going back to where we were last year, just now looking at the forward reaction, because all those conversations we had about spontaneity and enthalpy and exothermic and all of that, those are ideas that we can now talk about as AP students. But guys, going back to sort of where we were at this time last year, so guys, we understand, well, maybe I should ask it as a question. What determines, fundamentally, what determines if a collision will be effective? Right, but relative to this, what, and magnitude and all, but bottom line is, what has to be true for a collision to be effective? It's got to get over the hump. Yes? It got to get over the hump. That means it's got to be properly oriented and it's got to have enough energy to get over the hump. How much energy is that? Activation energy. Right, in this case it's 134 kilojoules. But guys, the answer is activation energy. So, what can we do to make reactions go faster? Well, one thing we can do is we can increase the magnitude of the collisions. If we increase the magnitude of the collisions get over the hump easier, the reaction goes faster. What's another thing we can do to speed up a reaction? Well, we can make more of them collide more often, because if they're colliding more frequently, more collisions get over the hump. But guys, what's the third thing we can do to make the reaction go faster? Drop the hump. And guys, you may remember that last year we brushed into this, but we didn't talk about it a lot. Now we're going to talk about it a lot. Guys, what can we do to drop the hump? Add a catalyst. So guys, let's talk about it, then let's look at them. So in order to do this, guys, what we need is to be able to drop the hump. And that's what catalysts do. Catalysts drop the hump. So what is a catalyst? A catalyst is a substance that changes the speed of a reaction without undergoing permanent change. And guys, the functional, just a second, Brent, the important word here is permanent. I would underline that. They can change, but in the end they don't. So guys, as you're getting into this, let me just explain to you what we're going to do. I'm going to lay out for you all the things that you need to know about catalysts. You're about to find out there are fundamentally two types of catalysts. So these are going to be sort of your reference points that you can build on. But then, guys, what we're going to do is we're going to look at each one of these individually. We're going to look at diagrams. We're going to look at videos. It'll be a good thing. Let's not go there yet, because that's not always what they do. It doesn't. It gets more of the hits over the hump. It doesn't change the energy. It just makes more effective collisions because it cuts down on the number of ineffective collisions. So, time out. How about if we learn about this before we get freaked out about what we don't understand? I know this is crazy. All right. So, guys, generally this is the deal. Catalysts affect the reaction rate by decreasing the activation energy for a reaction. How on earth could they possibly do that? They create a new mechanism. That's the answer to your question, Brandon. And guys, it's not in the notes. You may want to add that. By creating a new mechanism. And guys, as you write down those words, by creating a new mechanism, given what we've done over the last couple class periods, that should be extremely meaningful to you. And I'll show you what this means. But guys, that's the important thing that kept us from talking about this last year. Last year we just said drop the hump. And if you asked me last year how, I said we'll talk next year. Well, now it's next year. So guys, that's how they do this. They create a new mechanism. So what does that mean? Well, what are mechanisms made of? Elementary steps. And guys, that's how catalysts functionally do their thing. Catalysts create new pathways, new ways of reactants turning into products. And these new mechanisms, which are collections of new elementary steps, have different activation energies associated with them such that the overall activation energy of the reaction drops. Now, if your follow-up question is, how do they do that? My answer is, I don't know. And so guys, this is the point where I just need to be honest with you. I do not know anything more about catalysts than what I'm about to teach you. Okay, I'm seriously pushing right up to the edge of the cliff in terms of my understanding of catalysts. I never had a catalytic chemist as a professor. And you guys all understand that, right? The things that you learn in college are completely different depending upon the research emphases of your professors. You can take general chemistry from two different professors and it's a completely different class depending upon what they care about. So, guys, I know very, very little about catalysts. So if you want to do the deep dive on this, that's awesome, but don't look to me because I got nothing. So, that's exactly why... Amen, brother. That's why we have PES on the test, because that idiot from Indiana, it's his research emphasis, and he's got pull with the AP people. Okay, so, but guys, fundamentally, the idea is this. It drops the hump. How does it drop the hump? New mechanism. So, guys, what I'd like to do is show you an example. And so, we sort of said this, that this happens by creating a different pathway, and this then increases the value of K. You know what, maybe you don't even need to write that down because you're never going to say that out loud. So it may just be distracting, I don't know. But guys, what I'd like to do is show you an example. Before we do, let's talk about the two types of catalysts. Are you guys okay? Are you caught up okay? Okay. So, guys, this is going to sound familiar. So the two types of catalysts, one are what are called homogeneous catalysts. You may remember from general chemistry the triangle where we talked about homo and heterogeneous materials last year. What does homogeneous mean? Same all the way through. So fundamentally, guys, what this means is a liquid reaction catalyzed by a liquid catalyst, a gaseous reaction catalyzed by a gaseous catalyst. It simply means that the catalyst is in the same phase as the reactants. Typically, these are gases with gases and liquids with liquids. Generally, what happens here is the catalyst is consumed as a reactant. And you're going, wait a second. It says up there, nothing happens to them. It's reproduced as a product. So it goes in as a reactant and comes out as a product, and the net change is zero. It's not a spectator. It's none of those. So it's not an intermediate because it's doing chemistry. But, no, the intermediates don't do chemistry. It's not a spectator, my bad. It's not a spectator because it is doing chemistry. It's actually the opposite of an intermediate. And I'll show you what I mean in just a second. Not yet. Are you guys caught up? Are you caught up with the words? You okay? Okay, so guys, if you want to write this down as a clarifying thought, try this. So let's talk about intermediates. If we're talking about intermediates, we have A plus B yields C, C plus D yields E. That's an intermediate, right? C is an intermediate. Is that okay? Guys, don't confuse that with a catalyst. So, how is a catalyst different? Well, it goes like this. A plus B yields C, and then C plus D yields A and E. We still have an intermediate. C is the intermediate. Who is the catalyst? A, because A goes in and then A comes back out. So guys, intermediates are created and then consumed. Catalysts are consumed and then created. Do you see the difference? So intermediates are created and then consumed. You never know they're there. Catalysts are consumed as reactants and then created as products. So they show up on both sides of the reaction. So guys, how do we handle that then? The way that we handle it is this. So functionally, this reaction is just B. No, it's not. Guys, functionally, this reaction is just B plus D yielding E. Right? Is that okay?
Wait, why is it?
So we've got A and B going in, A coming out, so B gets with D and it produces E. So how do we represent A, the catalyst? We put it above the line. That's typically the way you represent catalysts, is you draw them above the yields arrow, showing that it is both a reactant and a product. It's a catalyst. Are you sure? Go ahead.
So, the catalyst can be chemically changed and all that as long as it comes out as the same thing.
It is chemically changed. It's a reactant, and then it's a product.
Does that have to, as long as it comes
Yeah, no. This is just homogeneous catalysts.
so long as it comes out the same?
So long as it comes out completely unchanged. Whoa. That was fun. Yeah. Oh, no. That's the point, and that's exactly why because in lab, your catalyst will be a homogeneous catalyst. Just a moment, I got to fix my board. Okay, what? You know how scared we are of anything, always and never, right? But no, that doesn't help. We're going to go with yes. If it goes in and comes out, it's a catalyst. But guys, understand, and Matt's not liking this because Matt knows some things about this from his time in California, I think. Guys, this is only part of the picture. There are also heterogeneous catalysts. Guys, heterogeneous catalysts are obviously catalysts that are in different phases. Typically, guys, these tend to be solids. Specifically, and don't ask me why, but guys, where'd it go? Platinum and palladium and nickel. If you follow my laser here really quickly, platinum and palladium and nickel tend to be wonderful heterogeneous catalysts. Don't ask why, because I don't know. And yeah, and actually, did you guys hear about that? So have you guys heard of a catalytic converter? If you don't know what a catalytic converter is, it sits in your exhaust system by your tailpipe, by your muffler. And what it does is it actually, it's a catalytic converter is this chamber in your tailpipe that's full of all these little ceramic beads that are coated in platinum, and as the exhaust from your car flows across them, it actually catalyzes some reactions that cause the gases that are coming out of your engine to further react with oxygen, making them less polluting. Well, guys, literally in a catalytic converter, you've got beads that are coated in platinum, and platinum is actually right now more expensive per ounce than gold. And so, did you guys see this in the news? Like 4 or 5 years ago, Canyon School District came back from Christmas break, and somebody had broke into their bus garage and take a hacksaw and cut the catalytic converters out of all of their buses for the entire school district. Yeah, because you rip them open, you melt down the beads, and you've got thousands of dollars worth of platinum. So somebody broke in and stole all their Yeah, absolutely. What? I don't know if they caught them. But guys, what we're going to do, we're going to think, and I know I'm distracting us, but guys, when we think of heterogeneous catalysts, we're going to understand them to simply be a surface upon which reactions take place better. Okay, so guys, what we're going to do then to round out the day is we are going to look at examples of homo and heterogeneous catalysts. Because I have no idea why our days are going so long. I think we're just talking too much, but I enjoy it and we're okay. So, but again, I think we're going to hit break again. Is this just making you guys grumpy, or are we okay? We're okay. All right. I know. So guys, let's do homogeneous catalysts first. You guys have all heard of the ozone hole, I hope. Guys, if you haven't heard of the ozone hole, that's good, because guess what? We fixed it. Guys, it turns out that back before global warming was a thing, back before Al Gore saved the planet, guys, there were university scientists. Thank you for chuckling, man. The guys, you've been in California. You know what I'm talking about. So, guys, back in the day, this is the 70s. This is before there was global legislation that we no longer participate in about trying to keep our planet healthy. Guys, there were some university professors that were flying weather balloons up into our upper atmosphere, and they were finding that there is a blanket of ozone, O3. It's literally, remember when we looked at it when we talked about resonance structures? It's bent and it's 3 oxygens. Guys, there's a blanket of ozone that surrounds our Earth that actually functions as a protective blanket that holds in good stuff and re-radiates bad stuff. Well, guys, it turns out that at our poles, there was a hole in our ozone layer. The reason is because the Earth spins, and as it spins, like a centrifuge, those gases tend to collect at the equator, and there was a depleting amount of ozone, and that ended up being a hole up at the North Pole, the ozone hole. Well, guys, they figured out why it was happening. To our credit, we fixed it. Guys, this is what was going on. This is actually the life and death story of ozone. Guys, ozone O3, looking at the red line with me, ozone O3 is a very, very reactive molecule. And up in our upper atmosphere, there is ozone, but there are also oxygen atoms. And when an oxygen and an ozone run into each other, if you follow the red line, they form 2 oxygen molecules. That happens all the time. It's fine. Our ozone layer, for who knows how long, has been able to offset that loss of oxygen. Let me zoom out a little bit. Guys, look at the activation energy for that process. The activation energy for that process as O3 and O react together is almost as great as the amount of energy in total that's lost. It's a huge activation energy. That reaction happens ridiculously slow, and as a result, there are other naturally occurring processes that replenish our O3 concentration, and we had a constant blanket of O3 protecting the globe. Well, guys, it turns out that that reaction between O3 and O is actually catalyzed by chlorine atoms. And this is terrifying. So, guys, here is, and are you familiar enough with this that I can zoom out and draw? Can you see it? Okay. So, guys, here's what we learned. I don't know why my mouse keeps freaking out. Guys, what we learned is this. We learned that if you throw a chlorine atom into this mix, it creates, well, let me say it this way. Chlorine catalyzes this reaction. We're not going to worry about how. But what we do know is this. It's a different mechanism. How do we know that it's a different mechanism? Because it's homogeneous. Chlorine is a gas, oxygen and ozone are gases. The other reason we know that it creates a different mechanism, notice the humps? Each one of those humps represents the activation energy of an elementary step. And we now have a mechanism that has at least 2 elementary steps. But guys, look at the activation energies for these elementary steps. They are 2 orders of magnitude lower than the uncatalyzed reaction. All of a sudden, the presence of chlorine takes this relatively slow decomposition of ozone and just throttles it up. And guys, the presence of that chlorine makes this reaction of ozone and oxygen so fast that ozone is just being gobbled up in the atmosphere. But you see the terrifying part, right? What happens to the chlorine? It comes back out. Can we just keep going? Guys, it comes back out. And they actually did the math. I have no idea how they figured this out. But in the end, on average, they were able to predict that every chlorine atom in our upper atmosphere destroyed about 1,000 molecules of ozone before it finally got tied up in some competing reaction and got taken out of action. Guys, this chlorine was amazingly destructive to our ozone layer. So the question then becomes, where was the chlorine coming from? Hairspray. And refrigerants in our air conditioners. Guys, and maybe you've heard of this. They're called CFCs. Yeah, they're chlorofluorocarbons. So guys, literally the stuff that is in your air conditioner at home and your air conditioner in your car used to contain what are called CFCs, chlorofluorocarbons. And it used to be, guys, back in the 70s, you would have an air conditioner repairman come to your house because your air conditioner is not working right. And what this guy would do is he would twist this valve and he would just release all of the CFCs in your air conditioner out into the atmosphere. They would literally just bleed the system and then repressurize it with new CFCs. That was the common practice when you were servicing air conditioners. And then, guys, aerosol cans. It used to be that your hairspray, the propellant in there was actually the same stuff that was in air conditioners, and we were just bleeding chlorine into the atmosphere by the metric ton every day. And so we ended up passing as a global community legislation that said we can't do this anymore. And guys, we actually got the chlorine out of the air. You guys, I don't know if you've ever had an air conditioner service now, but guys, these people are super, super careful. Like, they actually, if they come and they need to recharge your air conditioner, they have two tanks. One is a recapture tank, and the other is the new CFCs, because they still use things like CFCs. They can't off-gas them. It's got more fluorine and less chlorine, but it still could be a problem. And guys, by law, they have to capture those spent CFCs, and they actually have to weigh their bottles in and out. And if you can prove that they've been venting these gases to the atmosphere, they will fine that company to the point where they'll put them out of business. It's no screwing around. But it worked. We got rid of the chlorine and our ozone hole is gone. That's pretty cool. Go ahead.
And there was no political side to this science, like Democrats where chlorine is destroying Republicans where it's not.
I'm sure there was, but this was back in a kinder, gentler day when these people actually used to get along with each other. Yeah, I mean, back when I was a boy, I mean, it used to be that senators, when they weren't in chambers, they were out having dinner together. They were truly colleagues, even if they disagreed. We now live in a culture where we're so afraid to offend each other that we forgot that people can disagree and still like each other. And that's sad. So, guys, you good on that idea? We're okay? All right. So those are homogeneous catalysts. Guys, oh, wait, I don't. Let's talk heterogeneous catalysts. So, and I don't know how I'm going to do this without let me try this. If I just shut this, can I click? Can I draw? Okay, guys, I'm going to stumble through this, but I can't use my mouse anymore, so I offer no guarantees. So guys, now we're going to go heterogeneous catalysts. This you need to get in your notes. When we talk about heterogeneous catalysts, there are two terms that you need to know. One of these terms is the word adsorption, and that's not a typo. So, guys, when we talk about the function of a heterogeneous catalyst, now you're thinking solids. Platinum, palladium, nickel work really well. Don't know why. But we're thinking a solid, typically, interacting with a liquid or a gas. Understand, it doesn't have to be. There can also be liquid heterogeneous catalysts. There are actually some reactions that are catalyzed by the presence of water. But for our purposes, we're going to talk about solids. So, guys, when a solid, a catalyst, acts on a reaction. It functions through a process that we call adsorption. This is not absorption. It's not like a sponge absorbs water. This is what is called adsorption. It is simply the initial interaction between the solid and the reactants that are being catalyzed. I think I'll be able to show you a video unless this goes horribly wrong. And then, guys, so it's the process of the particles binding to the catalyst. And this process of adsorption happens at places called active sites. But Mr. Knappenberger, what makes them active sites? I don't know. Ooh, guess what we're going to do last? Enzymes. Yeah. I want you to know, though, several years ago, when I taught my students about enzymes, it got my YouTube channel shut down permanently. I'll show you. Yes. Yeah. I know, do it. You'll be fine. Guys. I know, and I didn't post it because I learned my lesson. All right, so guys, you got the notes. You understand that adsorption is that initial binding between the catalyst and the reactants, and this happens at active sites. So guys, what I'd like to do, if this, I don't know, but this is what it looks like. Are you guys all caught up? So guys, it goes like this. Okay. So
a specially prepared metal surface of nickel or palladium contains active sites, symbolized by the blue spheres, at which a surface reaction can occur. When ethylene and hydrogen are exposed to this surface,
I really want to be able to pause and talk. I really can't click on anything. Oh, maybe. Oh, yeah. Nice job, Daniel. No, I can't click. Oh, I can two-finger click. It doesn't. Okay, guys, I can't even. Okay, here's what we're going to do. I get the sense that the problem is this stupid thing. So. Okay, now, no. Oh, crap, no, I'm really stuck. Guys, let's do. Yeah, I think that's what we're gonna do. But I don't know how to handle that relative to recording. It doesn't matter because I'm gonna have to restart my computer anyway. I'll just do 2 recordings and then I'll blend them together. So why don't we take 5? I'll restart my computer and I'll come back. So guys, the thoughts that we have swimming around in our head right now are adsorption and active sites, and we've got this idea of heterogeneous catalysts. So guys, I know this video at first glance is like, but then if you really think about it, you start saying to yourself, you gotta be kidding me. So watch.
a specially prepared metal surface of nickel or palladium
So what did they do to specially prepare it? I don't know.
contains active sites, symbolized by the blue spheres, at which a surface reaction can occur.
I think we can say this, though, that these active sites are simply, not simply, but they are places on the surface that have unique polarities. Because all of this happens through intermolecular forces. So I think we can at least say that. What makes them active? Their polarities. How do you do that? Don't know.
When ethylene and hydrogen are
Okay, so here we go. So guys, over here, we've got an ethylene molecule. It's C2H4. It's important to remember that these are sp2 hybrids, so there's a double bond in there. Okay? What? Okay, and then diatomic hydrogen, right? Okay, so here we go. What do you notice about the diatomic hydrogen? It's stuck to the catalyst. Why? Polarity, magic, gods, we don't know. Little elves, we don't know. But guys, it's stuck to this. We do know it's intermolecular forces. What do we call that sticking process? Adsorption. That guy's just been adsorbed.
exposed to this surface, they are adsorbed in a process called chemisorption. The H2 molecules dissociate into hydrogen atoms.
Why? Right. So guys, look at what just happened. These hydrogen molecules were not just adsorbed, but something else about the polarity of this surface weakened the bond between the hydrogens, causing them to dissociate. But also notice that the same polarities that attracted the hydrogens also attracted the ethylene. And these molecules are attracted but still free to move.
Bound to the surface, but able to move about on it. When an adsorbed hydrogen atom encounters an adsorbed ethylene, it may add to one of the carbon atoms, forming a new CH bond.
See how that is an issue of orientation? That the surface holds that ethylene molecule down. And as it does, it increases the likelihood that these free-roaming hydrogens would hit that molecule at one of the carbon ends in such a way that it'll bond. But it gets worse because, guys, the hydrogen bonds to the carbon, changing the polarity of the carbon and releasing that carbon atom from the surface of the catalyst. Come on. That's how it works.
A second hydrogen atom then adds to the other carbon atom.
And then it gets released. That's crazy sauce. But guys, this is seriously the way that the catalysts work.
Forming ethane, which dissociates from the surface.
Right, and so that's 45 seconds long. And it's, hey, guess what? Hydrogen sticks. And oh, by the way, so does ethylene. And oh, they break apart. And oh, they run into each other. And oh, that guy sticks and gets let go. And that guy sticks and gets let. And they make, I mean, guys, this is like magic. It's like magical. And they turn it into something so mundane. But guys, the chemistry that's going on behind this is just mind-boggling. And it's all about polarities and intermolecular forces. So those are heterogeneous. You guys okay? Okay, so now guys, let's do this very quickly. Enzymes. Guys, this is important because some of you, I can see into your futures. You are going to be taking what was literally my favorite class in college, except for astronomy. My astronomy class was actually my favorite class in college because it was taught by a guy named Chick Woodward. Can you picture Neanderthal man? That's Chick. This guy is seriously crazy ripped. He's about that tall, hair down to his shoulders, big old beard. I mean, seriously, he looked like the missing link. And he's a PhD astrophysicist spending his days trying to find out what's in the middle of the Milky Way. Brilliant guy. And a hockey player. And so he would go on hockey tournaments over the weekend and come back. He'd be all cut up and like open wounds and all this crazy. And he was awesome. Anyway, that was actually my favorite class. My second favorite class was actually this one. Just about changed my major. No, organic was horrible. No. But guys, here's the sad reality. You have to do this in order to be able to get to do this.
What is that?
biochemistry. Guys, this is, as chemistry students, this is where this all just, it's crazy. Okay, I can tell you. No, okay, so this is off the record even though it's being recorded, okay? But you know where I stand in terms of my faith. Guys, you don't know that my brother is a devout atheist. He wants to believe but can't. And we've had tearful hour-long conversations about why he can't bring himself to believe, because he can't accept faith because he sees it as a weakness. Anyway, so biochemistry. This, and I'm a year ahead of him in college. He's a pre-med major. I'm a chem major. I'm doing classes a year before him. I'm taking biochemistry. He came over to my apartment in college. He's reading through the books that I'm studying, and we're learning about what is called the blood clotting cascade. It's simply the chain reaction of things that keep you from bleeding out when you cut yourself. And all of these fascinating things about why is it that your blood doesn't clot when you don't have a cut, and why is it your blood does clot and create a scab when you do get cut. And guys, it's all about enzymes, and it's all about proteins, and it's all about activation energy, and it's all about what's called the blood clotting cascade. And my brother was reading over this as I was studying it, and he turned to me out of the blue and he goes, "You read stuff like this and it's hard to believe there isn't a God." And I was like, whoa, really cool. Of course, it didn't go anywhere. But, guys, seriously, this class is bordering on spiritual. It's crazy, crazy cool. So when you get to biochemistry, you're going to love it. It's an awesome class. Unfortunately, you have to go through the hell that is organic chemistry in order to get to heaven. But, yeah, Dante would approve. So, guys, let's talk enzymes, shall we? So, guys, when we talk about enzymes, I bring it up because it's important to your understanding of biology, which is where a lot of you are headed. So, guys, enzymes are biologic catalysts. No, so really, you understand what catalysts are, things that change the rates of reactions. But in biologic systems, catalysts are everywhere. Catalysts turn on and turn off so many reactions in the human body. And thank goodness they do, because if they didn't, women would be in labor every day of their lives. Pitocin. Never mind, you'll learn later. But guys, understand that there are so many biologic processes in your body that are just waiting to happen, and they ain't happening because they ain't been turned on, and they ain't been turned on because the enzymes aren't there. Guys, these things are everywhere. So, they are biologic catalysts. And guys, the thing that's crazy is they're stinking huge. A molecule of enzyme has a mass on the order of 1 million atomic mass units. If carbon weighs 12, that's 100,000 carbons. Guys, these molecules are ginormous, ridiculously big and beautiful, literally. They're proteins. You guys know that, right? Enzymes are proteins, long chains of amino acids. But guys, when we talk about the process of enzyme catalyzation, there's two terms that you need to know, and you may see these on the AP test, so we should share them. One is substrate. Substrates are the things that enzymes are acting on. So these are the molecules that are undergoing the reaction that the enzyme is causing to happen. And then guys, the other term that you need to know is what is called the lock and key model. Again, I hate this for the same reason that I don't like that video that I just showed you. Because it takes something magical beyond belief and turns it into something so simple that it loses its magic. But guys, this is what is called the lock and key model. The lock and key model is a neat fitting system in which an enzyme is specially shaped for a particular substrate to interact with it. Guys, this is crazy cool when you get into the middle of it. No pun intended. But that's what happens. The substrate fits into the middle of the enzyme. But it literally fits like a lock inside of a key, or a key inside of a lock. Guys, what we find out with these enzymes is these enzymes have these amazing shapes. And it's not just their shapes, it's also the surfaces of these things and the polarities of the surfaces of these things that are shaped such that molecules fit, the substrate fits into these enzymes in exactly the right way in order for reactions to happen. And guys, regardless of what we do after the AP test is over, we are going to watch this one. This is an amazing video. It's called The Origami Revolution. It's a Nova special. 20 minutes of it was actually shot at BYU. BYU has an amazing composites engineering program. And they are figuring out how to take things like Kevlar and get it to fold in these amazing, amazing shapes. But this entire video is about the power of folding in the world, the universe. And frankly, the guys at BYU, the guys and gals at BYU that are doing this, frankly, the thing that they're doing, which is so applicable right now, is they're figuring out how to make bulletproof shields for police officers. So they can reach into their trunk and grab this handy little package that's kind of about the size of your notebook and go think, and this thing folds out into a self-standing bulletproof shield that you can hide behind. Yeah, it's not quite, it's not like unfurling a sheet, but the idea is fascinating. But guys, the beginning of this is really cool because there's a company that has actually figured out and written software that not only can do origami on its own. Have you ever done origami? It's crazy, but what you can do with this software is you can feed it any shape. Doesn't matter how complicated it is. You can feed it any shape and hit plot, and it will take a printer and print on that paper all the lines that you need to fold on in order to get that paper to turn into that shape.
Yeah, I've used it. It's called Capacura, right?
I don't know. But guys, it's crazy, crazy cool. But the thing that they're doing with it is this. They're using it to build proteins. So through the same logic, if you can figure out the sequence of amino acids, you can then take that chain of amino acids and let go of it chemically, let go of it, and it'll clump into a ball, and they can make that protein, that chain of amino acids, clump into any shape ball they want by changing the amino acids in the chain. They're making enzymes. So literally what they can do now is they can say, here's a molecule, and we want an enzyme that perfectly fits that molecule. And they can designer make a chain of protein, a chain, and they can let go and it goes bang, and it's exactly the right shape to fit onto that molecule. It is, guys, this is the cutting edge of what drug therapies are going to look like. Because imagine if you could make a molecule that could grab a hold of a cancer cell and not let go. They're getting towards that. It is unbelievably, so we will watch this video. And that's the problem. Yeah. So guys, what does this look like? Well, ready? This is how they take something unbelievable and turn it into something stupid. Here's the enzyme. Here's the substrate. Gosh, they match. And oh, it caused a reaction to take place. Guys, don't miss the magic because of the pictures. So how did I make it more magical? No, sparkles, good answer. No, so this is what I did. I found this video. I'm such an idiot. So guys, so lock and key model, right? I said, wouldn't this be more magical if I could put it in motion? There's the enzyme. There's the substrate. They match. A reaction. And then I put it on loop. So it goes backwards and forwards and forwards and backwards. And then I realized that if you watch this long enough, it sort of becomes soothing and meditative. And so I played Enya in the background. I can't, because that's when they shut down my YouTube channel, because they found the 30 seconds of Enya. And I would like to say, for the record, I did not buy the Enya album. It was my wife. No, there's a ton of shame being a guy with... Oh, no, I can't own that. I know, see? But, guys, seriously, allow me to do this. Because even this makes me sad. Let's try this. Let's Google this. I know. So guys, this is more like it. Oh, you know what? Actually, wait a second. Never mind. This is cool. Oh, I hope I didn't delete this email. I'll bet I did. I just got this morning. Trash. Right there. Where did it go? 3D. Guys, these are enzymes. Yeah, well, no, that's the... So this is the lock into which a key could fit. And guys, each one of these little corners and points represents a different atom. And each one of these little lines right here, you see how it kind of looks like DNA? Each one of these lines right here represents an intermolecular force existing between two charged points on this string. And the thing that's crazy is you could grab one end of the string and the other end of the string, and this will stretch out into one chain. One long chain. Imagine if you've ever tried to untangle a rope. Imagine trying to untangle that. But guys, this has two ends. And if you could grab the two ends and pull it apart, this is just a really long chain. And when you let go of it, it will always snap back into that shape. Why? Because of the size and charge and polarity of all of the amino acids that make up the chain. Now guys, what happens if one of those amino acids gets swapped for a wrong amino acid? Then it disrupts the entire shape of the molecule. You guys have done transcription and translation in biology, right? If you get one of those proteins wrong, it can completely disrupt the shape of the molecule, making the entire molecule worthless. And then you get things like sickle cell anemia and diseases like that that are simply diseases that are caused when your proteins aren't shaped right because they didn't get the right amino acid sequences. Because biochemistry is, and this is all the stuff you learn in biochem. It's really cool. Anyway, what somebody did, these are actually, and they're not all amino acids, or not all, I'm sorry, they're all proteins, but they're not all enzymes. Like this is insulin. This is what insulin looks like. This is hemoglobin, the stuff that makes your blood cells red. By the way, you guys know why your blood cells are red, right? Because, yeah, but in the middle of this molecule, and I looked for it but couldn't find it, there's an iron atom. And that iron atom is actually the thing inside that cleft that causes hemoglobin to grab onto oxygen and transport it. So literally, your blood turns red when there's oxygen in it because that iron and that oxygen basically forms rust, and rust is red. That's why the blood in your veins that you can see on the surface looks blue, because the oxygen's gone. It went to your muscles, and as a result, you don't have that rust-colored product. Anyway, so that's insulin. Anyway, so basically, guys, what happened is some group went through and built, like what does it say? They 3D printed the last 7 molecules that won Nobel Prizes. It's kind of cool. Anyway, all right, so guys, all of that to say, just a minute, Daniel, all of that to say, we've got kind of a sense of what's going on. We understand enzymes, lock and key. Guys, here then is your homework. But guys, in addition to this, I need chapter 15 summaries.